Okay, so I'm starting right away. So there are five codes. What we are supposed to do, I will tell you. So this is the first code, and this code is doing what? So initially we are defining A is equal to -3 -2 1 0. B matrix is 0 3, it's a column matrix. C matrix is 0 1, it's a row matrix, and D matrix is equal to 2. So you keep on writing what you have to do. Okay, the steps, and this video also I will upload. You can check there. So as soon as you run this, all the outputs will come in the command window. So as soon as you run this, this is what you are going to get. So I will just explain what are the steps. So num_den, numerator denominator, it is there. So ss to tf, ss to tf means ss stands for state space to transfer function. So it is called a state space method or state variable method, both are same. So state space to transfer function, provided ABCD matrix is given to us. So in that case, we are defining what will be the numerator and what will be the denominator of the transfer function. Now the numerator is actually 2s square plus 9s plus 13, and denominator is a square plus 3s plus 2. So that you can see here, numerator is, so the last line sys underscore tfm, tfm stands for transfer function model. So sys underscore tfm actually gives you this 2s raised to 2s square plus 9s plus 13. So is it understood that how it looks like? So if num_den is given, so num is 2 9 13, so that has come to 2a square 9s 13, and denominator is 1 3 2, that comes to a square plus 3s plus 2. Is it understood? Any of you please respond. Who all are there? Is it understandable how we have got the transfer function? Okay, so you just tell me, because I cannot see your whatever you are writing, I cannot see. Just say yes or no, that will do. Okay, so this is the first thing you have to do. Now the second thing what you have to do is make D matrix equal to 0. Make D matrix equal to 0. Okay, can you just tell me what is the type of transfer function it is? So there are three types of transfer function. One is called as proper, one is called as strictly proper, and one is called as improper. Can you tell me what kind of transfer function is this? What is the order of the system? Hmm? See, please answer. I cannot see your answers. So what is the order of the system? Transfer function, whatever is given, if it is CS by RS, what is the order of the system? Hello, anybody there?
Yes, sir.
So please answer the question so that I can go forward. What is the order of the system? What is the order of the system? Order is nothing but the power of the denominator equation. So denominator equation is s square plus 3s plus 2. What is the characteristic equation? It is s square plus 3s plus 2. And order of the system is nothing but whatever is the order of the denominator equation. So it's a second order system, and characteristic equation is s square plus 3s plus 2. So whatever is sys underscore tfm, it is actually generating the transfer function. So transfer function cs by rs is 2s square plus 9s plus 13, and denominator is s square plus 3s plus 2. So characteristic equation is s square plus 3s plus 2 is equal to 0. Now what will be the next step? Next step, what I'll do is, so all these things you have to show and you have to explain. So next what I'll do is I'll make the D matrix equal to 0. Okay, I asked you whether it's a proper transfer function. What is the definition of proper transfer function? Numerator polynomial should be having lesser degree than the denominator polynomial. So denominator polynomial is having highest order as a square. Numerator is also having a highest polynomial as in a square. So numerator and denominator, both cases, highest order is a square. That means this is called as a strictly proper transfer function. Okay. So how can you make it a proper transfer function? What is meant by proper transfer function? Order of the numerator polynomial will be lesser. That is called as a proper transfer function. And what is the improper transfer function? Improper transfer function you cannot generate by state space method. Improper means numerator order will be more, denominator order will be less. That is called as improper. So initial case we have kept the D matrix as 2. So exactly what part of the matrix changes what in the transfer function? That is the study we want to do. So now I'll make what? I'll make the D matrix as 0. Okay, and just check what change it brings into the transfer function. So just check here, numerator and denominator num den. So num is 039 and den is 132. So if you are changing the D matrix, it does not change the transfer function. Oh, sorry, it changes the transfer function. It does not change the characteristic equation. Previous case when the D was 2, then also the characteristic equation was a square plus 3s plus 2. Now that D is 0. Now also the characteristic equation is, somebody is asking something, just let me check. Okay, somebody is asking the session will be recorded or not. Yes. Okay, so this is what change you have to see, that if I have made D as 0, in that case you will be finding that the order of the numerator is reducing. So this is the effect of the D matrix, direct transmission matrix, and you can find the same thing if you are designing the companion form, whatever realization we had done. So first we had got the transfer function. From the transfer function we had done a realization, circuit realization. So you will see. So if D matrix is there, in that case the order of the numerator, order of the denominator will be same. And if D matrix equal to 0, in that case order of the numerator will be less than order of the denominator. Now what you do is you just take a negative D matrix. So D matrix element is -1. So just check what it comes. That -1 will come in the numerator. So all the numerator terms are becoming minus, like this. So this is what D matrix does to the whole system. So generally if we keep D matrix as 0, what we will find is we will find a good, that is a proper transfer function. Proper transfer function means numerator order is less, denominator order is more. So this is how the B matrix is helping. Now we know what is the transfer function. Transfer function actually is equal to C into Si minus A inverse into B plus D. So C and B, this both matrix, both element you cannot make 0. So just एक बार B का सब element 0 करके देखो क्या आता है. Okay, so C into Si minus A inverse into B plus D, and that is the transfer function. There's the actually formula for the transfer function. So now what I have done is I have made all the elements in the B matrix as 0. So this is not going to give us any transfer function. Yeah, you can find out system transfer function is all 0. So now make B matrix as something and make C matrix as 0. So if you are making C matrix as 0, then also there is no transfer function. We cannot find any transfer function like this. Okay, so all elements in B and C matrix cannot be 0. In that case, there will be no transfer function. So some non-zero element should be there. At least one element in the transfer function should be non-zero, like this. Now here is coming the most important thing. What is the elements in the A matrix? Okay, so this is whatever you are seeing. This is actually called as a controllable canonical form. So all the theories and everything is given here in this book. This is a book of Ogata. So you will be finding there are generally, if transfer function is given, that is yz by uz, from here you can find out 4 different types of system representation. So first one is controllable canonical form, second one is called as observable canonical form, third one is called as diagonal canonical form. So how can we find controllable canonical form? It is shown here. So you have to remember what is the transfer function. In the transfer function you have to see how it looks like. So it is given in Z because all these things are calculated in Z domain, but for S also the same thing. So instead of Z you have to read S, so everywhere it is S. So Z raised, so S square, so S raised to N. What is the coefficient of that? It is 1. So A1 is the, suppose it is Z square plus A1Z plus constant. Okay, and B naught Z raised to N, so highest power of S. So instead of Z you have to read S. Highest power of S in the numerator is having the coefficient of B0, and then as the power of Z is reducing, coefficients are changing from B0 to Bn. Okay, so B0 into S raised to N plus B1 into s raised to n minus 1 plus b2 into s raised to n minus 2, likewise it will go. Okay, and if the numerator is having lesser order than the denominator, in that case that b0 zn term will not be there. In that case it will start from b1 s raised to n minus 1. So our case also the same thing like this. It is a square plus something of s plus constant, and numerator it is something of s plus constant. So you can find out here it is a square plus 3s plus 2, and there is no a square term in the numerator. Okay, that means if you see compare with this, you'll be finding that the b0 term is equal to 0 for our case. So in this case you can find out controllable canonical form directly. So this is how it is given: x1 k plus 1, x1 k plus 1 you have to read as x1 dot. So these are all given in discrete domain. There's a book of discrete Ogata, but continuous domain also it is like this. So how to write the controllable canonical form? So it is 0 plus 1 plus 0 like this. Second term it will be second row it will be, third term will be 1. So first row second term is 1, second row third term is 1, likewise it will go up to n. The nth term will be equal to 1, and for last line it is -an minus 1 minus an minus 2 up to minus an. So what is an? If you see just the next part, what is an? If you see this, it is actually looking big, but it is not at all difficult. So just check what is an. An is nothing but the last term. Okay, so whatever is the lowest power of s. Okay, here you can find out what is the value. So s raised to 0, that is actually coefficient of an, like this. And a0 is the coefficient of s raised to n. A1 is the coefficient of s raised to n minus 1. So in this case, whatever we are finding, sorry, in this case, whatever we are finding, that is our an. An is nothing but if you check this. Okay, so in this case, an is equal to 2 and a1 is equal to 3. So likewise. So hence it will be -3 -2 1 0. So whatever is coming from here, this is controllable canonical form. And how to calculate yk? Okay, whatever is the C matrix, this is calculated as bn minus an b0, bn minus 1 minus an minus 1 b0, likewise. So this is something I will solve a numerical and I'll give it to you, or there is a numerical here only. There is a numerical here only in the fourth or fifth page. I'll show you that. You'll understand how it is. So it's a very simple small numerical. It looks only big. Just check this. Okay. Just check this. So instead of z, you have to read s. So consider the following: if it is s plus 1 and s square plus 1.3z plus 4. So how to write it? So it is 0 1 and minus 0.4. So this 0.4 comes here, minus 0.4, and this is minus 1.3, and this is 0 1. This will be 0 1, and this is that an minus b1 in 0 and something. So after some calculation it becomes like this. So this is the first canonical form, controllable canonical form, and second one is observable canonical form. If you are just taking the transpose of the controllable canonical form, it becomes observable canonical form. So in this case, the C11 it comes to B like this, and the B01 it comes to C like this. And if you're taking the transpose of this controllable canonical form, it becomes observable canonical form. So it is very easy actually. You can take a screenshot and you can keep with you. So only instead of S you have to, sorry, only instead of Z you have to read S. Okay, so what to see? To see is first very important thing, that D matrix is equal to 0. Even if we are making D matrix something, that is not going to change the transfer function. Okay, so system transfer function is the same, a square plus 3s plus, it will change the transfer function, it will not change the characteristic equation. I'm sorry. So characteristic equation is always same, a square plus 3s plus 2. That means s plus 1 into s plus 2. That means there are two roots. One is s minus 1, another is s minus 2. So the system is perfectly stable. Okay, so with A matrix, if I change A matrix, so from -3 if I go to -4, so this is something, how to change the transfer function, how to change the denominator, just see. Okay, now as I have changed the transfer function, as I have changed the A matrix from -3 to -4, that this -4 actually is reflected here, and this will become +4, because while doing the companion form we have seen that the system is actually having a negative feedback. That's why whatever positive here, that will become negative in this case. So this transfer function is a stable transfer function because everywhere in the denominator there is positive. Okay, now let us do one thing. Let us make this thing, okay, minus 3, and you will see that this minus 3 will reflect at the denominator. Okay, still the system is a stable system. Okay, and make this D matrix is equal to something else, D matrix is equal to 0, and you will be finding that this is a very strictly, sorry, this is a proper transfer function like this. Now what you do, make this minus 3 as plus 3, okay, and you will find that denominator will change, minus 3s plus 3, and you are finding a square minus 3s plus 2, and a square minus 3s plus 2, if you do the roots, okay, so roots of a is equal to roots, so we had the fifth code, and the fifth code is actually about find the roots. So in this case, or sorry, state representation, not the fifth code, but yeah, so m is equal to roots of 10 if you do. So in that case, it will be giving you the roots like this. Okay, so you're finding that both roots are 2 and 1. So both roots are positive. Both roots are positive means the system is going to be a system is going to be, both roots are positive, positive in S domain. That means both roots are lying the right side of S plane. So here only we can add, in the code only we can add this one line, and we can find out what are the roots of the system. So just run this thing. So fifth, fourth or third, I think, what is the code number of finding roots? This is actually the code number 3. Okay, so that also we are executing here. So what we are finding is the roots are going to be positive. Roots are going to be positive means system is unstable. Just we have made this minus 3 as plus 3. So this minus 3 minus 2 1 0. This is actually a controllable canonical form representation. And now again I have made this 3 as minus 3. So if you run this, you'll be finding that roots are going to be all negative. Just check here. Okay, so in this case I have made this 3 as minus 3. If I'm making it as minus 3, then what I'm finding is characteristic equation is s square plus 3s plus 2, and in that case s plus 2 and s plus 1 are the denominator polynomial, and if you're finding the roots from there, you're finding it is s is equal to minus 2 and minus 1. So just by changing this minus into plus, so again you do this. Okay, so this was the first element of a matrix, you made it positive, and you found that roots are becoming positive. Now again the second element I am becoming positive, so this minus 2 I have made as plus 2, and just see what are the roots. Okay, so in this case we are finding that one root is positive and another root is negative. So one root is positive means the system will be unstable. And what is the transfer function you can find here? So transfer function, you are finding that this has become minus 2. Okay, so if there is any negative in the transfer function, sorry, any negative in the characteristic equation, any negative in the characteristic equation will lead to a positive root. This is what you have to understand. So every element in the ABCD matrix, how they are affecting the transfer function, this is what I am telling you. Okay. So again you can see like this. So all these cases you have to show. So first case, this is the case. I'll just give you another brief recap what all things you have to do. So those who have joined late, they can just check. So first start with this minus 3 minus 2 1 0, you run it. Okay, as soon as you are running, you are finding that there will come numerator and denominator. So numerator and denominator both are having same polynomial. So this is actually called as a strictly proper transfer function. Why? Because D matrix is non-zero. Okay, this is the first thing. And what are the roots? Roots are minus 2 and minus 1, because characteristic equation of the system is s square plus 3s plus 2. This is the first case you have to show. Second case, make D matrix as 0. So now in this case, when D matrix was 2, this was a proper transfer function, strictly proper transfer function. Now as I have made D matrix as 0, it will become a proper transfer function. Proper transfer function means the numerator will be having lesser order than the denominator. So denominator is having order 2. This is the system transfer function, that means CS by RS, and numerator is having order 1. So this is a perfectly this is a proper transfer function. So this is how the D matrix is affecting. Now you can check B and C matrix, all elements you can make 0, and you'll be finding that B and C matrix, as soon as you are making 0, you'll be finding transfer function does not exist. If you are making B matrix as negative, let's see how it affects the transfer function. B matrix is negative, then also it is characteristic equation is same, you can find. So whenever I am changing B matrix, it is not actually changing the characteristic equation. Characteristic equation is same, that is a square plus 3s plus 2. And this 0 also you can make as 1, and let's see how it changes the characteristic equation. So changing B matrix will not change the characteristic equation or will not change the eigenvalue. So these are actually the eigenvalues, or these are called the poles of the system. So changing B matrix, all are reflected in the numerator like this. Okay. So changing B matrix will not change your transfer function. Transfer function will change, but characteristic equation will not change like this. Changing C matrix, if I make 0 and minus 1, yes, I think it will change so it also does not change the characteristic equation. So as soon as you have changed the C matrix, 0 and minus 1 you have made, that is also not changing the characteristic equation. So characteristic equation is something which depends totally on the A matrix. Okay, so B and C matrix changing is not changing the characteristic equation. You can see it is s square plus 3s plus 2. So all these things you have to very clearly write in your journal with every experiment, with every steps. So just take one change some part of B matrix, some part of A matrix, and you can change. Now, most important thing, let us change A matrix. And as soon as you are changing A matrix, you will be seeing that it is changing the system stable or unstable, because A matrix is called as a state matrix. Changing A matrix will change the whole eigenvalue, and eigenvalues are the heart of the system stability. Okay, so whatever you are finding roots of the denominator, that is nothing but the poles of the system, and that is actually should be all staying in the left hand side of S plane. So what I'll do is this minus 3 I will make as plus 3. As soon as I'm making it plus 3, I'll find that the characteristic equation is changing and the roots are becoming positive. Okay, so roots are now 2 and 1. They are positive roots, hence system is unstable. So this is the first element change. Second element change, you can do that. So in this case, as soon as I'm making minus 3s plus 3, both the roots are going in the right hand side. If I'm making the second element as positive, then you are finding one root is positive, one root is negative. Again, you can change from 2 you can go up to 20. So by increasing, let us see if the root position change. No. So as soon as you are changing the second element, one element will be negative, another element will be positive likewise. Okay, so this was the original case, minus 2 like this. Now the third element, that is second row first element. Now second row first element we will change, but before that let us go back to the original case. So this is the original case, first row is all negative, and now the second row. So this one, if I make minus 1, and then you will find that the system is changing its course. Okay, see that this second row first element from positive, if you are making it negative, then also it is generating some kind of positive root. So this 0.5616, because of this the system is becoming unstable, and you can check the characteristic equation is also changed, s square plus 3s minus 2. Okay, then this 0 if you are making suppose 3, let's see what it gives. So the 0 element, actually I have changed 3, and you're finding the same thing, one root is positive, one root is negative. So this thing I am making it positive again. So for different cases of each row element, you have to find what are the stability. So likewise, okay, so minus 3 minus 2 1 0, this was the proper case, because this is the, I told just now show you, this is actually the controllable canonical form. So this will give me a stable response. So this was the first code, and actually I have done the code number 3 there also. Okay, so what is the code number 3? Code number 3 is like this. So let us do the code number 3 also, because code number 3 is already shown to you, because root was not there in this first equation. But let us do the code number 3. So here the same thing as input, and let us find out what are the roots of characteristic equation. So real part of the roots. So here actually there's a problem, because I had to find out the roots of the. So here actually there are two roots. So in this case, I'm actually finding the real part of one root. root 1. So there are two roots, but I have found. So whenever there are two roots, both are real. So there is no point finding what is the real part of it. So, so there is no problem. So actually, this last time, this last part, I am actually uh, commenting because that is unnecessarily giving some confusion. So no problem. So I have found both the roots and both the roots are coming to be negative. That my system is stable. So this code number 3 and code number 1 with the root, they are kind of the same. We have already done it. So there is no problem. Let us do code number 4 and 5 because second code is little different. So far we had been giving ABCD matrix and we were finding what are the transfer function. Now we will do reverse. So code number 4 also the same thing we are doing, but what we are doing is actually we are plotting the impulse response and the step response. So up till this point, that is num den ss to tf, that means state variable to transfer function sys. So up till this whatever I'm selecting now, okay, so up till this it is the same code as code number 1. So as soon as we are getting the transfer function, as soon as we are getting sys, okay, so the sys is there. These two lines, actually these two lines are just to convert the numden into that s form. Okay, so only numerator denominator is there. So let us see actually what are the execution steps. So command window will be having the result. What does each of the step do? Okay, so all the these things are coming, results are coming, so no problem. Okay, so this sys comma tfm, what does this thing do? So this sys comma tfm actually converts this numerator and denominator into a s domain transfer function. Okay, so if you are just allowing, so if you are removing the semicolon, means you are allowing. Okay, so let us not plot the graph immediately. So what I'll do is I will cover the plot part. I will not execute the plot part. So figure 1 and figure 2, I will not execute that. Rather, I will execute the first few lines. I'll comment it. The comment is not functioning here, so I will better put a percentage sign here. Okay. So let us see what exactly is doing. So ABCD, as soon as I am giving ABCD, I am entering myself. So I have kept it to a 2 by 2 matrix. And then what is sys is doing? So sys is actually doing the same thing. Initially, sys is taking into account the ABCD matrix together. Whatever ABCD matrix initially given, it is not understood as a state space. So whenever you are writing sys is equal to ss ABCD, that means in this case you are actually trying to find out a system with transfer function where ABCD matrix are taken as A matrix as state matrix, B matrix as input matrix, C matrix as output matrix, and D matrix as direct transmission matrix. So this line is very important. Sys SS ABCD means you are instructing MATLAB to consider A matrix as a system matrix, B matrix as an input matrix, C matrix as an output matrix, and D matrix as a direct transmission matrix. And then you are finding whatever transfer function you have found from ABCD, that is that from that formula C into Si minus A inverse into B plus D. From there, you are trying to find out what is the numerator. So numerator actually 3a square plus 18s plus 27, because we are finding this 3 is there. So whenever the D matrix is existing, it is non-zero. In that case, we will be finding that numerator and denominator will be having same order. Okay, I had shown you just previously that you make this D matrix as 0, and you will be finding the order of the denominator will be higher and order of the numerator will be lesser. Okay, now what you are doing is, now you are actually found num and den, and after that you are actually finding sys underscore tfm. So sys underscore tfm gives you this. Otherwise it was only num and den, because we are habituated in seeing the transfer function in s domain. So initially in num and den it was written as 3, 18 and 27. You can check it is written as 3, 18 and 27, and denominator is 1, 3 and 2. So this sys underscore tfm is actually converting this numerator and denominator into s domain. Okay, now we have transfer functions. We know what is cs by rs. Now cs is equal to, you take the rs in the right side, and you just substitute what is impulse and what is step, and directly we can find out what is the response. So there are two responses coming for this transfer function, and one response will be impulse response, that is the first figure, figure 1, and figure 2 will be the step response of the system. So now let us wait for this. So both the graphs you have to show for different cases. So what are the different cases you can take? So this is a step response and this is the impulse response. So impulse response means we are giving impulse at the input t is equal to 0, and after that we are removing the impulse, unit impulse we are giving. And after that what you're finding is the amplitude or energy is decaying. So this is kind of a natural response of the system. So this is the impulse response of the system. Which system? 3s square plus 18s plus 27 divided by a square plus 3s plus 2. This is cs by rs. Okay, cs by rs equal to this. So cs is equal to rs into this whole transfer function, and then you have substituted rs equal to 1, and you have found out whatever is the cs. That means this whole thing, it has to be split into partial fraction, and after partial fraction you have to take the inverse Laplace transform, and that there you have to substitute t from 0 to infinity. In that case you are going to get this kind of curve. This is called as impulse response. What is meant by step response? Again the same thing, this thing. So cs equal to 1 by s into this. Okay, so 1 by s into this, so denominator will be s into s plus 1 into s plus 2. So again the partial fraction, and after partial fraction you have to take inverse Laplace transform, so that is ct. In that case you have to substitute t is equal to 0 to infinity. Likewise. So now what we do is see the amplitude is almost equal to 13. Now what we will do is we will just make the D matrix equal to 0. Okay, so this is code for response. So this is code number 4. And how to check different things we have to see for unstable system, for stable system. So first thing we have made D is equal to 0, and we have to find out what is the transfer function. So as soon as you are making D is equal to 0, it will be a proper transfer function you can find out. So here numerator is, there is no a square term, there is only s term, so 9s plus 21, and just check that amplitude has reduced a bit. Okay, previously the amplitude was above 12, so in between 12 and 13. Now here, as you have removed this direct transmission part, you have made direct transmission part as 0. In that case the amplitude has reduced a bit, and in case of impulse response also the amplitude has reduced a bit. Okay, so but this system, both are stable system. Here you are finding, though the amplitude is increasing, but it is not increasing and going towards infinity. It has already reached a steady state, and so we have found that there is kind of a step response. A step response area under the curve is kind of finite. It is actually a power signal. It is not a energy signal. Okay, energy signal means, so the first one, impulse signal, is an energy signal. Why? Because total area under the curve is finite. Okay. And this signal actually is a power signal, because here it is kind of a step response. It is a power signal. Likewise. Now very important thing is coming. Now we are going to see a unstable response. Okay. So unstable response means we made what? We made this minus 3s plus 3. If you do this, now check what is the response. So from state variable to system stability, all those things we are finding. Okay. Now you will be finding the step response will be a unstable response. Unstable response means you will be finding some kind of increasing exponential, and you can check that. Okay. So what is the impulse response? Impulse response also you are finding. What is the amplitude? Amplitude you are finding something raised to 10 raised to 25. You can say, sir, it is coming below, but coming below at t is equal to 600. But before that, the amplitude went huge. Okay, so amplitude was something into 10 raised to 25. That means up to 600, the amplitude was huge. So this is kind of a huge amount of 10 raised to 25. You can imagine how big is that. Why that thing happened? So impulse response, step response, both are generating huge amplitude. Okay, so they are actually unstable system. That means huge energy is coming there. Okay, so with because you can find the with this 3s minus 3s plus 3. Okay, because this is not controllable canonical form. In this case, you found the roots were actually positive. You can find here a square minus 3s plus 2. So a square minus 3s plus 2 is a that means if you just do this, you found the roots are, one root is positive, one, or both the roots were negative actually. One root was plus 2 and another root was plus 1. Okay, so both the roots are positive, means it's a unstable system. Second case, what we have made is, so there are two cases with D. One case D is non-zero, another case D is 0. There are three cases with A matrix. Okay, three cases with A matrix means A matrix, the first row, first column is positive, all other things are as usual. Then first row, second column is positive. So this is also unstable response. Let us see what kind of instability it gives. So second element I have kept it positive, and we will find what kind of instability is there. Here also you are finding it is highly unstable. Okay, and it is going. So previous case when we made -3 as +3, at least it was coming down after a certain time, up after 600. But when we have made the second element as positive, then you are finding it is going towards. So it is too much. It is bigger instability compared to the first case. Okay. And impulse response also you are finding like that. So it is a bigger instability compared to the first case. Okay. So first element and second element in the A matrix, if it is in this form, that is first row you are writing -3 -2. Then if you are making it plus, then it is going to be unstable response. It is generating unstable response. Again, come back to this. So this is -3 -2. This is d is equal to 0, and let us see what kind of response it is. It is going to be a stable response. We will find as usual. Transfer function is a proper transfer function, and you are finding a stable response like this. Any value of, instead of -3 -2, any value you can take. Okay, so impulse response is area under the curve is finite, and this is also, you will say, sir, it is going towards infinity, correct, but it is staying at the one level, so it will get stable at amplitude 10. Okay, it is not going beyond amplitude 10, and that amplitude 10 will be maintained. That means steady state error is 0. It is like that. So instead of -2, you make it -20 and check what happens. Okay, so if you are making -20, but minus is very important. What is the value? That is not very important. Okay. So here also you are going to find a stable system. Here also you should find a stable system. You can find out. Okay. Likewise, you're finding a stable system, and there has come some oscillation in this. You're finding like this. Okay. So actually, the stability has reduced. When it was -2, stability was more, because whenever there is oscillation means there is more energy input in the system. And you found previous case, the impulse response was actually falling like this exponentially, but in this case impulse response also, it has become kind of oscillatory. So this -2, if we have made -20, stability is reduced a bit, but then also the system is stable. So let us make it -6. Let us see what happens. So if you have made it -6, then what happens? In this case, the stability will increase. So oscillation means there is more energy. More energy means instability. Okay, so if it is -6, you can see here. So stability is kind of increased a bit. Here also you are finding it to be. Okay, so here also you are finding stability is a little bit increased like this. So I will go back to the normal mode layout. It is default. I'm sorry, just give me some time. Okay, so in this case, it is coming like this. So what we have done? We have done is we have changed. This is from -2 to -6, and now make third element +1 as -1. And what changes does it make? We will see. So this +1 we have made it -1. In this case, also the system will become unstable. Let us see the instability. You can find here the graph is actually exponentially increasing. The system becomes unstable. So this is the step response. How it is found? That this +1 I have made as -1. Impulse response also is exponentially increasing, and just take here, it is 3 into 10 raised to 25. Okay, so this is a very big instability. So this element, as soon as you are making it negative, this element actually takes to the system to instability. So these are the codes that I had given to you. So the question was, I will show it big. So actually, I have explained the code number 1, 3, and 4. So code number 1, this was the code that we were converting the state variable into transfer function. That was the first thing. Third code was actually generating the roots, and if the real part of the root is positive, system is unstable. If the real part of the root is negative, the system is stable. So that I had shown. And then for every element in the A matrix, so A matrix is very important. A matrix is called a system or state matrix, not system matrix. A matrix is called a state matrix. Every element is important, and how is it related to the transfer function and stability? I have shown. There's actually controllable canonical form which is shown here. The first element, second element, they are actually the coefficients of s and constant. So depending on their positive or negative value, how it is changing. Last one is state transition matrix. So we have seen Si minus A inverse into so Si minus A inverse is called a state transition matrix. So how to find the state transition matrix? It is given here. So just copy it, and A matrix you have to define something. So A matrix is minus 3, minus 2, and 1, 0. And then for different values of t. Okay, so this is actually a state transition matrix for t is equal to 3. And we have to calculate, actually we generally in actual our numerical, we calculate state transition matrix in the form of E and T. Okay, but here actually we have to calculate the value, because E and T is not given in MATLAB. So here actually we are calculating the value directly. So value is nothing but at t is equal to 3, how much is the value that you are calculating. Now you just change it to t is equal to suppose 1, and you save, and you can run, and you'll be finding what is the state transition matrix at t is equal to 1, like this. Now if you are increasing the value of time, the whole system goes into the reducing mode. The state transition matrix value will keep on reducing. Just check. This is something what you are supposed to understand, that if I am increasing the value of time, that means the system is actually is a stable system, whatever A matrix is given. Minus 3, minus 2, 1, 0, this is the controllable canonical form state matrix. In that case, the state transition matrix value is actually reducing very fast. That means as the time is going by, all elements in the state transition matrix is actually, at least in the first column elements, their value is reducing. If I put t is equal to 100, then what happens? Let us see. So you can see it is 10 in 10 raised to minus 43. That means that time is equal to 100, state transition matrix almost equal to 0. Okay, so state transition matrix is very high initially. Substitute t is equal to 0. Initially, when the system has just started, the states have just started, you can check. State transition matrix is Si minus A inverse into B, Si minus A inverse. And if you take the inverse Laplace and substitute t is equal to 0. So this is the at t is equal to 0, what is state transition matrix? That is e raised to t n. Okay. Then 0 point, suppose 2, time is passed. So you are finding state transition matrix after 2 seconds. The values are reduced a bit. Okay, then suppose after 20 seconds, like this, and what is the value, like this. Okay, so state transition matrix is something which actually captures the states at different time. So as time is increasing, in this case state transition matrix value is reducing. We know that state transition matrix is given by exponential. So exponential is having highest value at t is equal to 0, and as time is increasing, the value actually reduces. So this is the fifth code, state transition matrix. How to find it? It is very simple code, that is A is equal to this, and STMAW. So this is the state transition matrix. STMAW. It's not. It's a just variable. You don't give STM, so STM might get mixed with some other variables. So STMAWE, I have given the name, and like that. Okay. Now the second code, the last thing I will explain is the second code. So what is the second code? Second code is the reverse of the first code. So in the first code we were giving ABCD matrix and we are getting the state transition matrix from the first code. Second code is exactly reverse. Second code you give numerator and denominator, and you are getting what is the ABCD matrix from there. So CLC clear all is there, and you can check what is the name of the code. The name of the code is num and den. So num is 1 2. 1 2 means s plus 2, and denominator is 1 4 and 7, that is s square plus 4s plus 7. So if you're giving this, it is actually a, you can say it's a proper transfer function, and ABCD, all the ABCD 4 matrix will be given, and from numerator and denominator. So you can see here what is the output. So this outputs you have to show. So this is -4 -7. So you can check here now what is actually the first row and all. So this is again the controllable canonical form. So this is mine, or you can write this as 1 0 and -4 -7 also. Somebody can write as 0 1 -7 and -4. So all these things are there, and depending on that the position changes. So this is -4 -7 1 0, and in this case B is also 1 0, C is 1 2, and D is equal to 0. How can you get D? Now just change, make it a strictly proper, so make it 5. Okay, so in this case previously it was 1 2, you are finding D matrix as 0. Now you just make it as 5. Okay, just give any value, and you will be finding that D matrix will become non-zero now. Okay, you just check. Yeah, so D matrix has become non-zero. So whatever 5 you have given, whatever was the a square term in the numerator. Okay, so the C matrix has changed, B matrix also has, B matrix has not changed. It is 1 0. A matrix also has not changed. Okay, so depending on this D, depending on this element 5, what changes is changes your C matrix and changes the D matrix. So this is the sweetness of a state variable, that every position, how it is reflecting in the ABCD. This you are supposed to know. Okay. So if you, now this is a strictly proper transfer function, because now you find that numerator is also a square, denominator is also a square. You can just increase this thing. So instead of 7, you can make it just 10 or something. So now it is numerator is of order 2 and denominator is order 3, and just check what is the ABCD matrix. So very easily it will become a bigger thing. So it will become a 3 by 3 matrix. You can check. Okay. So now it is 5s square plus s plus 2, and denominator is s cube plus 4s square plus 7s plus 10, and denominator is all positive. You can find out all positive. That means roots will be all negative. So here also you are finding -4 -7 -10. So it can be also written as a 0 1 0 0 0 1 and -10 -7 -4. Okay, so whatever controllable canonical form you have said, just check here. It is 0 1 and -4 minus 1.3. So this is just a representation, and this is -4 -7 -10. So the last row has been reverted and brought at the top. So this is what MATLAB is following. So -4 -7 -10, B is 1 0 0, C is 5 1 2, and D is 0. Now what you do is make -1 at the numerator. So now make it a strictly proper transfer function, and this -1 that you have brought, that will be nothing but coming with D. But you will find that the A matrix, B matrix is not changing. So A matrix and B matrix are same. The changes have come in C matrix and D matrix. So this is what you are supposed to check, and you can find the roots also. M is equal to root of the denominator, and if you do that, you will be finding all roots will be negative. In this case, that means system will be stable. So these are all things that I had to tell you. So just keep on changing the different values of A matrix, D matrix, C matrix, and just keep on showing different cases. And for few cases, just show what is the step response and impulse response. So that is what I had to tell you. Few people have joined. Thank you for joining the session. So recording of this session will be uploaded shortly in